Well, good morning, everybody. And by good morning, I mean good afternoon. Good afternoon. Welcome to Ellensburg, Washington, USA. Thank you for joining us today, live. We have more than 300 waiting and ready to go. There'll be more that show up. Or thank you for watching this replay a day later, a week later, a year later, a decade later. I have no idea. But regardless, I'm happy that you're with us. Thank you for being here and being ready to enjoy this episode. The local time is 1:48, and we're going to begin our program. Session U, thoughts on resolving the Baja BC controversy with Robert S. Hildebrand at the top of the hour. That's a mouthful. At the top of the hour, about 12 minutes from now. So you know the drill. We're going to do some chit-chat here for the first 12 minutes, make a couple of quick announcements probably, and then and we're all good there. But I'm going to email Bob. Well, how are we doing here? Can I say hi to a few of you before I email Bob? Canary Islands, hello, Ram. And Steve's in the Netherlands and Springfield, Oregon, Prosser, Washington, Ottawa, Canada, scrolling, but I'll just try to grab what I can. Lake Chelan, Washington, Powell River, British Columbia. Thank you, 101 Rotary Power, 5x5 video and audio. Appreciate seeing that. Courtemanche, France, Morabina, Victoria, Australia. I think that's Victoria. I don't know. Dayton, Ohio, Göteborg, Sweden, Philomath, Oregon, Lake Ozark, Missouri, Billings, Montana, Urbana, Maryland, Coldstream, British Columbia, Okotoks, Alberta. Sorry, Alberta. It's easier just to call you Alberta, Gary. Wow. Come on. Twin Falls, Idaho, Los Angeles, California, Glasgow, Scotland, Grimsby, UK, Harwinton, Connecticut, Dorena, Oregon, near the University of Oregon, Fort Bragg, California, Muskogee, Oklahoma, QC, Canada. I think that's what that said, Renee. I'm sorry. Sarito, California, Backcountry Gary in Darrington, Washington. Hello, Gary. The Netherlands, that's Sipe from Eindhoven. Pittsburgh, Pennsylvania, St. Louis, Missouri, Laytonville, California. I'm on a roll. Michael's in Scottsdale, Arizona. Papagino's in the Selenian Block, Dallas, Texas. Windsor, Ontario. Okay, I'm getting carried away. I got to email Hildebrand. Okay, so let's do that. Copy the link. Give me a sec, would you please? Sending the link 3 different places for Bob. Even though I think he only needs one. It's coming from my Gmail. Okay, so fingers crossed. That invite goes out to Robert S. Hildebrand of Tucson, Arizona. Now we have 450 watching. Okay, all right, people are rolling in here. Happy February, first day of February 2023. Hello from Eastern Washington State. Okay, hello from Eastern Washington State, coming back at you. I guess I'm Central Washington. Utah, Lakewood, Washington, Mount Gambier, South Australia. Hello, Dags63. Oh, there's Garrett, the Dutch night owl from the Netherlands. Steinar is from Bergen, Norway. Antioch, California. Things have slowed down considerably now. That's easier to read. Tessa says hello from Hobart, Tasmania. Hurricane, Utah, Waikele, Hawaii, Marion, Virginia, another Alberta person, Amy, Dallas, Texas, Northeast Portland, Swansea, Wales, Wisconsin Rapids, Clyde Park, Montana, Firestone, Colorado, Ventura County, California, Deering, Kansas, Billings, Montana. I mean, I'm not being personal today, right? I'm not saying people's names, but I'm just kind of locked into the places, but it's not bad. How's the weather in Ellensburg? Oh, it's probably 30 degrees, but on my bicycle, it feels like it's 15. It's one of those raw days, overcast skies and everybody bundled up walking around campus. So I'll probably enjoy this. I'm sure I'll enjoy this session, and then I will clean up the auditorium, and then I'll pedal home real quick past Vindman's Bakery, and probably sit in front of the fire, thaw out, relax with Bijou the cat on my lap. Kyle's at the passive margin in Reston, Virginia. Kim's in big Baja, California. Sure, that's right. John says 15 degrees is warm. No, I understand. I understand. I understand. Thank you. I understand. Southwest Oregon. Terrific. All right. Well, no Hildebrand yet, but let's not panic, boy. Let's not panic. It is February. And we have 6 shows left. So I've got some of those guests lined up. Oh, there's Bob. Terrific. I have some of those guests lined up, and I'll announce that and announce a couple other things towards the end here today. Okay, Bob, terrific. I'm glad you're in the green room. Can you hear me, Bob? Can you wave to me, Bob? Oh my, are you kidding me? Oh, you can. Okay, thank you. I was about to throw a fit, Bob, seriously. Okay, all right. Bob's going to be working with the laptop only today, and that's our plan, and hopefully have less problems than we did on Saturday. But he's concentrating on sharing his slides right now. Hello to a few more of you. Columbia, Missouri. Hello from New Zealand, heading to 30 degrees C in the coming days. Thank you, Lynn. Some of you know via video Hannah Shamloo and Jordan Carey. They're in New Zealand right now at a conference. And so I'm curious how things are going for them. And I'm covering Jordan's classes here this week, which has been a pleasure. Happy to do that for them. London calling, that's Red Lester, he's a regular, or she's a regular. Sabers in Loreto, Baja California, Mexico, thank you. Aberdeen, Scotland, Huntington, Vermont. Pam's in the sort of sunny Bitterroot in Montana. Farmer Mark, hey man, he's from central Wisconsin. Okay, and Bob has shared a screen as well, so I see that in the green room as well. Bob, can you raise your hand one more time that you can hear me? Can you wave to me right now that you can hear me? Bob, can you wave to me? Thank you. Thank you. All right. Jeff says direct to you from Peru, and Kate's in Columbia, Missouri, and Amy's talking to more Alberta people. Amy has a kinship with all the Albertans. Is that what you say? Yeah, Cambrian kids from Cochrane, Alberta, if you must know. We'll talk about Alberta today a little bit. British Columbia a little bit today, and so on. There's Vindman's Bakery. This episode brought to you by Vindman's Bakery. You've got to love it. Jennifer is in Boise. Hello, Jennifer. Northwoods 3D says Wisconsin is well represented today, too. That's good. Nice. Don's in Elma, Washington. Everybody's talking to Vindman's. That's terrific. Montana is well represented today. Okay, everybody's all full of pride that their representative states and provinces and counties and cantons and other things are all represented. That's good. It's just terrific to have you all with us for sure. All right. Well, we're getting close to hot mic time. I guess I'll say few more hellos, and then I need to start concentrating. Bob, I'm going to do about 10 to 15 minutes of chalkboard, and then I'm coming to you. Okay? I'm still not sure he can hear me. Okay, all right. He's kicking back already. All right. Northern Exposure, he or she is in Kittitas County. Rachel's in the Netherlands. Jim's in Crystal, Minnesota. Lon is in Beaverton, Oregon. Eagle, Colorado. Lake Oswego, Oregon. Media, Pennsylvania. Texas. Tigard, Oregon. Tanana Terrain, Fairbanks, Alaska. Piedmont, Maryland. Honey Greg says this show is always an adventure. Yeah, that's true. I'm getting better and better with my blood pressure, but it's still a bit of a wild ride almost every time. So who knows what's going to happen today? That's part of the fun, right? None of us know what's going to happen. We just go for it. Hi, Ashley. She's in Seattle. And Camino Moraine, I don't know where that is. Camino Island. Is that a moraine? I guess I should know that. Colorado Springs, Colorado. Omaha, Nebraska. Okay, I got 2 minutes. So please allow me to concentrate, get my head right, and we will begin this session in 2 minutes. Thank you for joining us. Hot mic. Okay. The viewers know who Bob is. This is part 2. You're setting the tone. You're working with your chalkboards briefly. Keep it fast. You're going to do some drawing very quickly, very open-ended. You have scissors, you have paper. You're going to use the scissors and the paper. It's going to feel hokey, but there's a chance it's going to be effective. So don't rush through it. Concentrate on what that is. And then we go to Bob. But you're starting with big ideas, and Bob is starting with big ideas, and then you're working your way down to smaller and smaller things. Start with the major messages. Save the announcements till the end. All right, you can do this. You can do this. Have the energy. Have the energy. Be peppy. Be smooth. Be brisk. Chalk and then scissors. Chalk and then scissors. Yeah. Just roll with it. You can just roll with it. Give into it, roll with it. Let's go. Welcome, everybody, to Ellensburg, Washington, USA, here on the campus of Central Washington University. I'm so glad that you're with us. I hope that you enjoy this session. Our guest today is Robert S. Hildebrand from Phoenix, Arizona, and you already know him. You watched the last show. That was Bob Part 1. This is Bob Part 2. And so to remind you, the previous show we've already done. On Saturday morning, we were talking about westward subduction and closing ocean basins, and we were talking about batholiths, some from subduction of an oceanic plate making arc magmas, and other batholiths, other plutons back in the Cretaceous from slab failure. That's in the past. Today, some of those concepts might come up, but that's not what we're doing today. Saturday was essentially a setup for Bob's thoughts on resolving the Baja BC controversy. That's today. And this is a Baja BC A to Z live stream series. And yes, there's just a few shows left. Here we are on February 1st, and we have 5 more shows after today, more coming on those remaining letters at the end of today's episode. But my job here is to kind of go back to the format we've had most of these letters, and that is I am going to spend 10, maybe even 15 minutes on the chalkboards, and also with scissors and paper, I'll explain, and try to just set up our discussion with Bob. Bob says he has less slides than last time. Bob says we are going to do a little bit of back and forth and converse about some of these concepts and hit some of the major themes that he wants to cover with us today. In other words, his major thoughts we want to start with when we get to Bob, and then we'll just see where it goes. So, what can I do to get us ready for that discussion? Well, remember now, Hildebrand is doing all sorts of compilations and synthesizing of incredible amounts of data. Mexico, the lower 48 in the US, Canada, and Alaska. And that will be happening again today. We're going far afield. We're thinking very, very large again today with Bob Hildebrand. But I want to remind us all that we've been dealing with 4 different models. The first model for building the Rockies, for dealing with explaining much of the geology of the American West, the conventional story has been 50 plus years of flat slab subduction. Warren Hamilton, Bill Dickinson. And these other models that we have been kind of looking at and listening to and visiting with the geologists behind these models are alternative models. Alternative models to number 1. And we're seeing all sorts of data that supports these alternative ideas and does not necessarily support number 1. Please remember that both the hit and run model and the fixed archipelago model, this is Basil Tikoff and Bernie Housen, brand new paper. This is Karin Siglock and Mitch Mahalanuk, a paper a few years old. And ribbon continent, that's Stephen Johnston 2 shows ago, and then Bob Hildebrand as well. All 3 of these alternative models embrace the paleomagnetic data and therefore have ramifications for building the Rocky Mountains. So maybe a surprise to you, we're going to talk a little bit about the Rocky Mountains today, even though we're thinking about Baja BC. As Basil says and has said numerous times, you got to be willing to take on the whole banana, the whole enchilada, the entire American West and all the mountains, not just take your pick. So that's where we're going again today. So if we take Bob Hildebrand, our guest today, we're down here with number 4. I think Bob has multiple ribbon continents, not just one. That maybe is one distinction between Stephen Johnston with 1 ribbon continent and Bob Hildebrand with 2, 3, 4, I'm not quite sure, ribbon continents out in the Pacific. We'll hear from the master himself momentarily. But what I want to do is try this big picture view from what I think I understand from reading the papers that were posted for today's episode. And then we'll go to Bob and he can correct, he can clarify, he can expand, he can do all sorts of things. So it's like we're doing Saturday's episode in reverse. I'm starting with my kind of major thoughts, and then we go to Bob, as opposed to the last show where we were with Bob most of the time. And then after we were done with Bob, then I added a few of my own thoughts and tried to kind of sort out what I was absorbing and experiencing. So Bob is very careful by email and also in some of his maps and his papers, very careful to say there are 2 key places in the American West that need to be honored paleomagnetically. The Carmax lavas today up in Yukon. Those are the ones that Stephen Johnston was talking about, Jane Wynn was talking about, Randy Enkin was talking about, and I know that Hildebrand's going to lean into the Carmax again today. Bob says, whatever model you have, please be aware that the paleomag of the Carmax lavas today up in the Yukon say that there was 1,950 kilometers worth of northward translation. So in other words, the Carmax are in Yukon today, but they were almost 2,000 kilometers to the south of where they are now. That has to be thrown into your model, says Hildebrand. He also says the Blue Mountains of northeastern Oregon, with rocks 93 million years old, have paleomag that says, again, we're way more than 1,500 kilometers of northward transport. So in today's Blue Mountains, that's stuff that has to be much further to the south as well. Throwing this out there for you, Bob, I did look carefully at Bernie's numbers, Bernie Housen's numbers from his brand new paper, and instead of 1950, he's got 1,400 kilometers. I don't know if that's a significant difference or not. And in Bernie Housen 2023 paper, the hit and run paper that's new, he's got 1,000 kilometers from the Blue Mountains instead of 1,760. This is intermontane, both of these guys, intermontane. Instead of just focusing on the insular, we're now dealing with the mega whale. And Hildebrand is an extra mega whale person, I do believe. Again, just setting things up for Bob. So the real thing I want to do with the chalkboards, assuming I'm still functional and comprehensible, that's not a word, comprehensible, what? I want to try this as quickly as possible. And believe it or not, I want to go back to last winter. Last winter, the alphabet series was the crazy Eocene. And I wasn't planning on it, but we were getting Basil Tikoff to be joining us 3 different times last winter. And Basil kept talking about the Cretaceous. And Basil kept talking about the Severe and the Laramide and building the Rocky Mountains. One of the viewers sent me this beautiful piece of artwork that I have in my office. I'm sorry, I can't remember who you are. So the visuals of the Severe, the visuals of the Laramide is something I want to revisit for today's episode because Bob does talk about those 2 things a fair amount in these papers for today. So if you're willing, let's do a quick trip down memory lane. This is last winter. We have a major hit of the insular superterrane. I know we've been away from that lately, but this is last winter. Major hit 100 million years ago of the insular superterrane. It hits roughly in the neighborhood of the western Idaho shear zone in Basil Tikoff country. There's a little bit of intermontane in there as well, but whatever. We have the major story from last winter of an insular major collision. That means that we have compression, and that means that inland of the big hit, do you remember the and then the fireworks afterwards, back in the Cretaceous? We had 2 different styles of deformation back at that time. We had low angle thrust faults that I'm coloring green here, where we have thin-skinned deformation and a bunch of thrust sheets being sent piggyback to the east, and we're building part of the Rockies that way. Overlapping in time, I guess, although I'm not still clear on that, maybe Bob can help us, is we have steeper reverse faults farther inland, and those steeper reverse faults allow us to have what we called block uplifts. I might write that out. Block uplifts of the Laramide. Parts of the basement, Cratonic North America, being lifted essentially vertically out of the ground to have this Laramide style signature of the Rocky Mountains. Whereas the Severe mountain building, last winter we thought it was all from the same event, was a very different style of building the Rockies. And the Severe stuff is a little bit further west than the Laramide. Okay, that's where we left it last winter. And by the way, that all shut down, that all stopped. The big number last winter, 53 million years ago. Do you remember? 53 million years ago, somebody turns that switch off. We stop building the Rockies and we start to thin and extend the crust. And we ultimately took those narratives into the North Cascades. That was last winter. Why am I talking about that again today? Because Hildebrand's talking about parts of that. Hildebrand says on a map, and this was a big moment for me, Bob, yesterday afternoon. After I tested the AV with you, I went home and I'm like, wow, that is quite a thought. I can't believe I didn't have that thought before. Here's the thought. Hildebrand says, where are these Laramide block uplifts? I'm going to use pink again, Laramide. This is a cross section. Now I want to do it on a map. Well, they are the main signature of Rocky Mountain uplifts in Wyoming, the main signature of Rocky Mountain uplifts in Colorado, and into Montana as well. Laramide block uplifts, big pigs coming out of the ground, big sows back shaking these layers of green jello away as they emerge and these big hogback type things come up. That's the story here. And to the west of those pigs rising, those block uplifts in Idaho, in southeast Idaho, we're into Utah now, are our thrust faults, our severe style, thin-skinned thrust sheets. And those continue through Glacier National Park. That severe style cluster of thrust faults, low angle faults, and making mountains by doing this kind of thin-skinned activity is heading up into the Canadian Rockies. Okay, what's the big revelation to me? Where are those Laramide pigs in Alberta? I'm embarrassed to say it, but I never really had that thought. Where are those Laramide uplifted blocks, those pigs in northern Montana? They're not there. All we have are these thrust faults. We don't have the corresponding uplifts. And so what Hildebrand is saying today, among many other things I'm sure, is that Banff and Jasper and this portion of the Canadian Rockies was not made in the Canadian Rockies. These mountains were made in Utah. This is a mismatched situation, and these green thrust faults belong down with their friends. And that allows, therefore, that makes it possible to send this rock more than 1,000 kilometers to the north. Okay, that may or may not work for you. If it does or if it doesn't, I'm going to use some scissors and try to say the same thing, and then we're coming to Bob. So this is the iconic map from his 2015 paper showing the Texas lineament and the Lewis and Clark line, and I'll let him expand on that. But what I want to do is take those two lineaments, line them up, and in the process, I'm taking these severe thrust faults in Canada and bringing them down to Nevada and Utah where they were formed. The Canadian Rockies were made in the US. That's essentially what we're saying today. Did that one work for you? No? Okay, well, how about this? A more simplified map showing the same thing. Texas lineament, Lewis and Clark. I'm going to try to do it looking through the back of the page. This is a mega whale and then some, right? We're not just talking about insular now. Hildebrand is saying if we restore the entire, this piece of paper, is restore it completely, we can get down and onto the paleomag and match up a bunch of other things. Oh, by the way, we suddenly have piercing points, which we have not had to this point in the series. I was going to do more, but I think I've made my point. So we're going to Bob Hildebrand, who I can't even see on camera right now, so this could be another problem, but we'll try it. We'll try it. We're going to Tucson, Arizona. Battery 100%. Well, let's see if we can find somebody down in Tucson, Arizona. Bob Hildebrand, how are you today?
Fine, thank you. Can you hear me?
I can hear you perfectly. I'm so relieved. How about me? Can you hear me?
Barely. No, I can hear you well, thank you. I can't see you, though.
Oh, God. All right.
I have you on another computer. I can see you on the other screen.
You're always full of surprises. Just when I think I know what's about to happen, I don't. Well, way to go. You got me off balance already, but I'm glad we're communicating, number one. So thank you for being with us yet again. And I don't know if you have any reaction to what I was just trying to do. did I make some mistakes, or do you want to just jump right in and make some kind of expand on some of the things I was trying to say?
No, I think probably I should drink more coffee because I'm going to need a little bit more velocity to deal with those things with you.
Okay.
Okay. No, I think it's good. I mean, you left out a few things, and one of the things that I would really like you to think about is when Bernie Hausen says 1,000 kilometers. That's like 1,000 kilometers plus or minus 500.
Right.
So It could be 1,500. It could be 500. And errors are really big on these paleo mag things. Like the CarMax 1960 or plus 700 or whatever it is. They're big, and it's important to honor the errors because most of the time they're 2 sigma errors. So it'd be 95% confidence that whatever it is was within that interval.
Good, and that's everybody's paleo mag, right? That's not just Bernie or somebody else.
No,
everybody doing paleo.
Pretty much everybody reports a 2 sigma. I'm not a paleomagnetist, but I think that they do. Whenever I check it out to see, it seems like they do. Yes.
Okay. Good.
So should I? No, I thought it was fine. I'd like to try to as we talked about, I'd like to do a little bit with the Baja BC concept at first, and then later on towards the end, I want to address your concerns about sutures, and we'll come to that later, and so hopefully people will hang around for that discussion.
Okay. Yeah, absolutely.
So let's because yes.
You want to go to some slides? Is that what we're ramping up for right now?
Well, yeah, I thought I might introduce the subject a little
good.
bit.
Well, let me bring your slide in, and it's totally black at the moment. Okay, so I'm going to hide it again. So you might have to share your screen slightly differently than you did because all I see with your shared screen is black at the moment. So I'll let Bob concentrate on doing something different with his shared screen. Remember, that's that. Okay, here we go. I'm going to bring in this one. Good. We have a beautiful photograph, Bob.
Oh, thank you. This is Peyto Lake, and it's in the Canadian Cordillera.
Okay.
And one of the main ranges, and I just wanted to first start out in Canada today.
Good, thank you.
Where a lot of things are that we're interested in.
Yep.
And I like the spot, so I thought I'd show the photograph.
Thank you.
So one of the peculiar things about the Canadian Cordillera that everybody seems to have noticed, but nobody has really done much with, is that's these 2 metamorphic plutonic belts within the Canadian Cordillera. You have I know my pointer gets real small, but it's really big for me still. You have the coastal plutonic belt over here. Mm-hmm. And then you have the what's known as the Omanika belt through here. Most of them are basically orogenic hinterlands with metamorphism, exhumation, and plutons.
Okay.
And everybody's known about that, and you can see this is from 2002 Monger and Price, but it's also was pointed out in the first Monger, Templeman, Cluett, and Price papers, 1982, and so forth, and so forth. But nobody's really done much with it. Mm-hmm. And I got to sort of spacing out at Ray Price's new map and some papers, and I realized that this is an area of Ray Price's last map in southernmost Canada. It's just north of the border, and there's a whole bunch of Bell Purcell rocks out here, Mesoproterozoic rocks in the west. And they're to the west, they lie dominantly to the west of the Bourgeot thrust. Mm-hmm. The plutons out here are dated to be 108 million years, but yet they cut the thrusts here. And these are refolded thrusts. They're not just simple thrusts. They're at least probably 2 periods of deformation, but 1 long period anyways. And then on this side of the fault, you have the Wapiabi Formation, which are Santonian, so 86 million year old marine shales. And they're juxtaposed across a single fault here. So this fault wasn't even active till after the Wapiabi Formation because it's just a sediment sitting there, and there'd be no reason for this fine-grained marine shale to be next to this big thrust fault, at until afterwards. So this thrust fault is younger than 86. So there's 22 million years between the thrusts, at least 22 million years between the thrusts here and here.
I'm with you.
And this seemed, to be somewhat problematic. And I wrote in some papers earlier that this was the Bell-Purcell Windermere lochthons, which are those things in the west. They're older than 108. But if you go over and you look at the North American platform terrace to the east, these are much younger.
Mm-hmm.
So these are incompatible. And then you come down to the Great Basin sector of North America, and you find that the North American platform terrace has 125 to 105 million year folds and thrusts, so things like the Canyon Range thrust. And then you go to the west. No, there's no thrusting at that age. It's mainly Middle Jurassic and Late Cretaceous deformation. So I suggested early on, I said, well, maybe the Omanika belt belongs back in the U.S. That would match up the thrusting. So, and this thrusting would have been from the severe orogeny. There's a bit of confusion around the world, and people use severe for thin-skinned in general, and then commonly laramide for thick-skinned. And I've tried to separate them into two different orogenic belts, because the severe is older and the laramide is younger, and the laramide has both thin-skinned and thick-skinned in my book. But that's how I'm just defining that term. So at any rate, these are folds and thrusts that are older than 108, probably 124, something like that, but you don't know until they're dated. So I then was reading some Phil King in his book on the tectonics of North America, and he talked about this Texas lineament, this area down to the southwest of the south and southwest of the U.S., and then the Lewis and Clark line to the north. And he used those two belts, which are not faults according to him, as dividing zones between the southern, central, and northern Cordilleras. And he noted that the geology in the south was different from the geology here. And of course, down to the south, you have a thin-skinned fold and thrust belt over here. And you can see, perhaps you can see the curves for the thickness of the sedimentation over here. Well, they come up and turn parallel to the Texas lineament. And then the next time you see those are way over here and adjacent to Utah. And then you can follow them up, and they go on up into Canada. So this is thick-skinned and thin-skinned. This is dominantly thin-skinned, and this is to the north is thin-skinned. Also, he noticed that the Basin and Range province, which you see here in Nevada and westernmost Utah, was offset and shows up again down in Mexico. Most of Mexico down here, and you can see them on this map here of this dam of the topography. So what I did is I said, why don't I just join these two lines and see what happens? And because then I'll be bringing the Omanika belt back to the south, where could match up with rocks. So let's line those babies up. And while I was thinking about that, I noticed that, there's a couple of magmatic belts. There's the Sonoran batholith and the Coast Plutonic complex have rocks that are the same age. There's a late Cretaceous, early Cenozoic swarm of plutons in both belts. And then I looked at all the paleomag. Here's the Carmax to the north up here, and it restores back down to here. I've plotted the error bars on here, by the way. The Blue Mountains here, restores back to about here, and so forth and so forth. The leaves, the Swakane gneiss, which I was pushing in the early days, matching up with the Orocopian Polona schists down here. So I thought, well, this is pretty good. All these things come down, seem to match up, and this magmatic belt will match up pretty well. So I looked at it again, and I said, look, if I match these two up, then I get the Miocene Basin and Range provinces here and here will line up. The Swakane Orocopia Polona schists, yellow here and here, they'll line up. Eocene magmatism, Eocene magmatism comes down to Idaho, Montana, picks up again down in Mexico. The porphyry copper belt up here in Montana, and then down to the south in southern Arizona and Sonora, and then this 80 to 58 million year magmatic belt. It will line up very nicely, and then of course there's King's original division lines here. So there's, count them, 1, 2, 3, 4, 5, 6 things that can be restored by moving this block 1,300 kilometers to the south. Nobody's got even one. People vaguely say, oh, I've got some detrital zircons that are out here and they might match up with stuff in the Colorado Plateau and so forth. But, it's kind of vague. And here's 6 right here off the bat. So I thought that was worth pursuing. The problem I had was I couldn't find the fault, just like everybody else.
Right.
And I said, well, and I kind of hemmed and hawed and did the best I could and said, look, they must be in the thrust belt, and that they're just difficult to recognize, and there's lots of faults there, and if we work at it a bit, we should be able to figure that out. And I left it. And I'd moved on to other things, as you've seen, mainly into the slab failure realm and the origin of continental crust and the peninsula ranges orogeny. Well, this reconstruction I had does this. It looks pretty much like this, and I published this, I think, in the 2015 paper. Swakane Oricopia here, joining up the 80 to 58 million year magmatic belt, which I felt was a slab failure belt. And these rocks here will move up into Canada and so forth. So I had the fold thrust belt and the movement here. Well, when I was working on my latest paper of the Western Interior Basin, I made a map of the Western Interior Basin, a figure, which shows the Cretaceous in green. And then I noticed that there were a whole bunch of isopachs. And isopachs, for those that don't know, are basically thicknesses, just measures of thickness. And so this bit of isopachs up in here, there's numbers going from, 40 to over 500 here. It would form a thickness curve that would look about like this. So from the bottom here up to this line is how thick it was. And then in the southeast, it would be much thinner. Well, anyways, if you notice the scale on this map, this is 500 kilometers. And just this little section here is just a little bit longer than 500 kilometers. So here it is blown up. So all of these isopachs streaming down here, and they get to the edge of the Cordillera or the foothills, and they disappear. And this is 500 kilometers of stuff. And these don't show up again 500 kilometers to the north or the south. Yet the normal accepted separation on the Tintina Fault, which is just to the west, is about 430 kilometers. So this is already more distance than the 430 kilometers, and nothing's matching up. And I've never particularly liked the piercing point that they had of the thrust belt to the north. But anyway, so I said, that's pretty peculiar. And then I noticed that the overlying formation, which is the Dunvegan. Now, the Dunvegan's a formation that was shed from the Cordillera as it was rising. It's what we call a clastic wedge. It's material that's being shed out of the origin. And this is some cross sections of the rocks from my co-author Janak Bhattacharya. And these things are conglomerates and coarse sandstones and things like that. These orange rocks, the yellow are sandstones, and then the green are the silty mudstones, and the grays are shales. So if you look up here in the right-hand corner, the alluvial fans, which are these orange units, they also just get truncated. This is the same area, by the way, as the other isopachs we were looking at, but they were an older formation. And then the shoreline, edge of the sandstones comes down like this. Well, this cross-section goes like this. So you need to come all the way out here to the west in this little diagram to get back to the alluvial fans, if it ran more or less north-south. But these facies are also truncated. So that got me to coming back again to the Carmax group. According to estimates of the paleomagnetism, It's shown in green here. They're about 1900, let's say 2000 plus or minus 600 at 70 million years. They're not a flood basalt province as most people suggest. They've been plenty of analyses done. We have them, both from Don Francis and Ryan at the Geological Survey. They're dominantly basaltic andesites, and even slightly more silicious trachyandesites.
Is that important that it's not flood basalts?
Sure, flood basalts you might want to relate it to the Yellowstone plume or something, but they're not the composition of the rocks that you might find in the Yellowstone plume.
Oh, interesting.
So we can come back to this later. I have a couple of figures that we can talk about this, but so yeah, the Columbia River basalts are what you get from the plume.
Okay, thank you.
From mafic rocks, anyways. So there's some of these that are tiny little green dots. You might be able to see them right between the word Tintina and trench. And,
yes.
and Randy Enkin has done Paleomag on at least one of those, and published it in that 2006 volume. Well, it's right next to the Tintina Trench. I mean, it's 7 kilometers from the Tintina Fault. This is a fault. It's a recognized fault. Everybody says 400 plus kilometers. Gabriel's originally said, well, it offset sedimentary facies 900 kilometers. And then he just the last thing he wrote, he said, well, it's still possible. Then you get down here to the Liard lowline, which I forgot to rotate for this slide. I apologize.
No problem.
And then you come into the Northern Rocky Mountain Trench, which everybody says North Rocky Mountain Trench and the Southern Rocky Mountain Trench. All the people that work there said, wow, there's no strike slip fault there. It's a normal fault. And they argue it fairly strongly. So we're going to look at a couple areas right around the Peace River. The Peace River comes into this reservoir here, and we'll look at a couple of things here, and just remember this reservoir and the Peace River. This is kind of a key dividing line in the Cordillera.
Thank you.
But first, I want to mention that if you go and look at Randy Anklin's data for bedded successions in the Cordillera, the Carmax group is here, and virtually, what I did was I took the youngest possible, or the farthest north distance for the Carmax group, in other words, the least movement, and maximum for the Carmax group, and I drew these purple dotted lines. Just they're lines of maximum and minimum movement. And if you look at this, you can see that every single one of these, going back to 90, is within error of the Carmax group. So, and this one Silver Creek, Powell Creek, I haven't gone back and looked at this lately, but I forgot what the difference is between these three, because they're all the same. They're different sites, I think, of the same unit. But so basically, in my mind, if you can understand and move the Carmax group, you've basically solved the problem, because you can move all of these will restore within error to the Carmax. It may be that some of these are older and have a little bit more transport, but the bulk of the thing can be solved by moving the Carmax. And the Carmax is right next to the Tintina Fault. And so it's 70 million years. And so the upper Nanaimo is pretty close as well. And it docks probably just 50 or just before 50 million years. Let's just use 50 to make it round numbers, because they do. You ever wonder why speed limits are in multiples of 5 or things? Why don't they say speed limit 73? Anyways, so the Carmax group starts at 70, it's pretty far north. By 50, it's dead. So by 50 million years, all of these units, which represent the hinterland, have poles that are consistent with those of North America. But the important point here is everything is within error. And Randy Enkin pointed this out in 2006. Everything's within error of the Carmax group.
So why, Bob, have I been saying 85 to 55 for Baja BC so long? Why do those numbers continue to be in most of these papers? Are you saying that's way too old to start Baja BC, 85?
No, I'm not saying that at all. I'm saying you don't know, because it's within the error of the Carmax group. Everything has error bars. That's what I was trying to tell you in the beginning. You got to take the errors, 1,000 kilometers plus or minus 500. So all you know is there's a 95% chance that thing was there at that time.
Mm-hmm.
Okay, that's all it says. I mean, that's still 5% chance it could be up here.
Yeah.
And stranger things have happened. So, but the point is that and like I said, these could have moved a little bit farther than the Carmacks, but not so much appreciably. I mean, a little bit, maybe 600-700 kilometers more. So there could be, but maybe not. You can't tell it from the data, is what I'm trying to say.
Thank you.
So starting at 85 or 90, it could, but you can't go to the data and say, oh yeah, look, it started then. All you can do is infer that it might have. So that would suggest that some more work might be needed to be done on some of these things and to try to resolve and work out some of these differences to get better precision.
Okay.
But anyway, 70 to 50. So that's what we're talking.
Okay.
So in the north, the Tintina Fault is really a well-developed strike slip fault, and it just follows. It's got a nice trench, and everybody agrees it's thing. But to the south is everybody argues that from the Northern Rocky Mountain Trench, Southern Rocky Mountain Trench, these are not strike slip fault. There's no strike slip fault there. It's a normal fault, and everybody has rocks that go across it and say, look, it can't be. And then you kind of scratch your head and you go, well, I know, but there's a minimum 500, maybe 1,000 kilometers of movement on the Tintina Trench. Where does it go? And everybody goes, well, I don't know. and then they throw up their hands and go, well, that's the way it is. Well, in the north, the thrust faults are 100 million years. And we know that because they're cut by the 99 to 93 million year plutons of the Peninsula Ranges orogeny. So all the thrusts up in this area, and then out in here, there's some at 120. But at any rate, the thrusts up in this area are older than the Tintina Fault, which has to be younger than 70 according to our model of having the Carmacks move on it. And in the south, however, the thrust faults are as young as 52 million years, and they postdate the Tintina Fault. So they're
younger than the Tintina?
They would postdate the Tintina Fault if they're 50, 52, 53 million years, and we want to have our movement go from 70 to 50.
Okay, I see. Thank you.
So they at least they'd cover the bulk of it, right? We don't know that the movement might stop at 55, 56, 54, 53. But we do know we've got a whole bunch of thrusts down here that are younger, that seem to be younger completely than any strike slip or any motion on the Tintina Fault. If it were to come through here. And I think that's the difference. I think up here, the thrusts are older, so you can see the strike slip fault. Down here, I think there are younger thrusts, and they hide, they obscure, they cover up, they bury the Tintina Fault down to the south. I think it comes right down through this trench. It's the same darn trench all the way through. It's huge. It's one of the biggest features of the world, the biggest on-land trenches in the world. And so it's not a small feature. So the first thing, and you can go up to this lake, which I showed you earlier, which is Williston Lake, and it's in the trench, and the Peace River is coming in here on the right, on the east side. And what you can find is that there are, as I said, 2 ages of thrust faults even. So here's these thrusts coming down from the north that are pre-99 to 93 million year thrusts and that are cut by the plutons. And you can see they come down here, and this whole belt gets cut off and truncated by this thrust here coming through here. These are Proterozoic Windermere rocks. They're classic rocks of Windermere that are Proterozoic. And it gets completely truncated. Here's a detailed map that was compiled from older maps by Margot McMecken at the survey in Calgary. And you can see the fault comes right up through here and carries on. And it sits on top of these older thrusts. So this is you can clearly show that there are 2 ages of thrusts just from the geometries alone.
And can you please remind me, the Windermere is older than the Belt Purcell?
The Windermere is younger than the Belt Purcell. It sits on the Belt Purcell, unconformably, supposedly, and sits beneath Paleozoic rocks. So
is there Belt Purcell beneath the Windermere there in that map?
Not that's known.
Okay.
Not that's ever been recorded.
Thank you.
And in a recent paper by a guy named Dinu Pana, who works for the Alberta Survey, he went out and he's been doing a bunch of stuff on the sly and looking at rocks, and he found he's got this band of deformed rocks right down the trench in the northern part of the southern Rocky Mountain Trench. And he says that, I'll quote him here, approaching the trench, bedding is gradually transposed into a steeply dipping foliation parallel to the trench. And it's got these sub-horizontal rods and fold axes. So all the linear things within the planar foliation are horizontal themselves. And the foliation is steep, and the rods in them are elongated. So there are things that have been stretched out in the fault zone here. And so he basically says everything has been rotated into parallelism with the trend of the fault. This is exactly what you'd expect with a major strike slip fault. Because, of course, first of all, a fault that is vertical, you can't extend anything or compress anything. It just sits there, and things
right.
on the side. But you can move it strike slip wise, and so that's that. When you see vertical faults, that's what you think about as strike slip, unless you have older faults that are rotated. But this thing's hundreds of kilometers long. So,
but you would expect that strike slip action to be older than 53 then.
Well, yeah, generally older than 53, 55. I mean, somewhere in that range, somewhere.
Thank you. I'm just trying to keep up. Yeah, that's good. Thank you. So
somewhere in there. So this is the current surface in the Rocky Mountain Trench where everybody says it's normal faults. It doesn't. From the fabrics, it doesn't look like normal faults. Let's put it that way.
Mm-hmm.
Then I looked at seismic, deep seismic, this paper by Firmer years ago. And I don't know how well you can see this, and I apologize, but I just didn't think of a really good way to redraft this or make it look a lot better. But down at the bottom here, maybe you can see my cursor. It's kind of small,
yes.
red.
Yes.
And down at the bottom there are these reflectors, and they're interpreted as the basal Cambrian, supposedly near the basement. And they go all the way across. There's a little bit of overlap in each one of these. So Chevron Mobile Flathead is here and here, and then the stuff here at the edge is over here as well. So, or PC belt is over here as well. But anyways, so you can follow this stuff down in the lower crust all the way west, and it keeps going west, keeps going all the way through, keeps going. And then all of a sudden it comes to the Rocky Mountain Trench and it disappears. It's gone. The whole section's gone. And I said, wow, that's interesting. So the surface, there's clear truncations, and down through the sedimentary succession in the crust, that's also doesn't carry through the Rocky Mountain Trench. That's just getting it more interesting by the day. So I looked up a paper by Chen, of which Steve Johnson is a co-author. This is one of the grad students, I think, in his department. And if you look at the mantle, here's the Rocky Mountain Trench. The mantle, the seismic in the deep mantle, the mantle topography, what Karen Siglock does, also shows, look at this, the mantle is different on both sides of the trench. So I said, okay, we got the surface, we got the crust, and we got the mantle. It's all showing that there's a major break here. I'm liking it. I'm really liking this idea. I said, look, this trench is turning out to be good. It is a big strike slip. So I looked carefully at the papers by Dinu Pana and Ben Vanderploem, and they date fault rocks. And so these, I don't know how well you can see these numbers, but these red ones are faults that they've dated: 52, 56, 51, 54, 52, 54, 52. And so that includes the McConnell fault, which is a big fault that separates the foothills from the main Rocky Mountains. And so other faults they've dated, here's a 99 and 103. These are probably just a relic fragment from the peninsular ranges of orogeny. Then there's some Jurassic ones, 163, 146, 162, and then a bunch in the lower 70s, 68 and lower 70s. And so it's as if you're juxtaposing all these different ages of thrusts. There's gaps of 20 million years or more, 30, 40 million years in some cases. And so I looked up the shortening estimate for rocks from the McConnell thrust to the east out into the foreland basin here, and it's 100, right about 100 kilometers of shortening.
Mm-hmm.
So I said, well, let's restore these rocks 100 kilometers. And that includes the Lewis thrust here. It's got a separate estimate of 100. Because you got to add up all the shortening on all these thrusts out in front of it, plus that one, and plus the rocks that are carrying. So everything comes back 100 kilometers minimum. Everything comes back past this dashed pink line, which is the Rocky Mountain Trench. And I said, oh, that's pretty interesting. So the youngest thrusts are what move all of these rocks past the Rocky Mountain Trench. So they were over here. These
I
here
see.
prior to the movement on the Rocky Mountain Trench. And then maybe the very last stages of movement, the thrust just moved them the last 100 kilometers over the top of the fault.
Huh? It's like a snowplow pushing snow 100 kilometers from where it was before, doing that compression, and that eventually kind of conceals some of the strike slip motion.
Well, I think it sits on top of it. Yeah, I think the last gasp of shortening or compression was the thrust over, or it's possible anyways. You know, so it's worth exploring. So here's what it looks like. These are cross sections by this guy Fuentes, who did his PhD here with Peter DeSalles at the University of Arizona. Here's the Belt Purcell out here. By the way, for those that don't know, it's called the Purcell Supergroup in Canada and the Belt Supergroup in the U.S. So most of us just refer to it as the Belt Purcell.
Thank you.
At any rate, and then you have a bunch of Paleozoic thrusts out here, and so then this is a restoration. This is a restoration of those thrusts. So if you come to the belt here, here's the belt tip, present day erosional surface. It's all the way out here. So all this is in front of it now, and all the way out to here. So here's 20 kilometers, and if you go from here, you probably got two of those, at least one, but 1.5 going out here. Whoa, let me back up. And then you got another 4 or so coming out here. So about 100 kilometers you could restore this cross section back to what he did. And they do this by bed length balancing. In other words, they just stick things end to end to end, basically. And then a little bit in the south, mostly in the U.S., is a bit of belt here. The belt, the Lewis thrust here. It's in a big synclinorium with all the thrusts out in front of it of Cretaceous rocks. And then it's got a Eocene, a later mid to late Eocene collapse thing here called the Kishinen Basin, studied by a number of people both in Canada and the U.S. This is what the Lewis thrust would look like, or actually does look like, because this is a photograph of it, not a digital mock-up. And it places rocks of the belt supergroup on top of the Cretaceous 4 deep, mostly shales and siltstones here.
Is that just another thrust fault in the severe stack, or is that more significant, that Lewis thrust fault?
This is a thrust fault that carries the Belt Purcell on it.
Huh.
It's a 50 million years thrust. It's not a severe thrust. It's a 50 million year thrust. I'll go back.
Yeah, I'm starting to lose it, I got to say. Like on my chalkboard stuff, Bob, I was visualizing all those thrusts doing their thing, and then we offset things up to Canada. But the chronology of that is not correct, I guess.
I don't know what you were thinking, but the thrust is dated at 52.
Okay.
That's
all right.
It's dated at 52. You know, I mean, it's got 100 kilometers of movement on it. So it seems like it overthrusts the Rocky Mountain Trench.
Thank you. Please continue.
So it looks like this. Okay, so this is a cross section from Kurt Constenius, who was at the Arizona. I guess he's retired now. This shows the original thickness of the belt allochthon up there on the Lewis thrust. And we know it had a band of Jurassic Cretaceous. We know it had to be this thick because the Jurassic Cretaceous is exposed underneath this younger normal fault basin here. So we know about how much was eroded off the top. Here's the present day topography. And so somewhere 68 kilometers of rocks were eroded from the Lewis thrust sheet after emplacement and during middle Eocene extension and exhumation. So past 50 some odd. Okay, maybe 52, could be 52 plus or minus 2 or 3, who knows exactly, but maybe just slightly older. And so when you look at the rocks just to the west of the Lewis thrust, shown here in red, there's nothing coarse here. There's no coarse debris in any of these units. Even the units that the Lewis thrusts over, there's nothing coarse. It's almost shales and siltstones. And so you kind of wonder, wow, we just had 6 to 8 kilometers of belt parcel eroded from this thrust sheet in pretty rapid fashion, because you know that the thing collapsed. You know that normal fault collapsed in the Eocene as well. So, but there's nothing out here. It's not there. And then people found out in the Bear Paw Mountains. The Bear Paw Mountains is a volcanic center, one of many Eocene volcanic centers. And underneath the volcanics out there, they found that the Wasatch Formation, which is a lower Eocene formation, contained boulders and cobbles of belt supergroup overlain by these volcanics. And the boulders and cobbles got finer grained as you went to the east. So here's good evidence that the Lewis thrust was being eroded in the early Eocene, lower Eocene. Then in the Highwood Mountains here, also beneath volcanics, they found boulders and up to 1 meter across of Archean gneisses and sandstones and Paleozoic carbonates, also between these beneath these volcanic rocks, these Eocene volcanic rocks. And they argued for a large alluvial fan spreading out from here. So we know the age that the Lewis thrust was in place. It's around 52, 53 million years, and it was eroded and had huge amounts of erosion, 6 to 8 kilometers of it, and was spread out there. So, but the reason I mention this is because some people have argued that it couldn't possibly be. These thrusts couldn't be 50 some odd million years, but it appears that they are. And one of the, yeah?
Can I interrupt again?
Sure.
The last slide is, so are you visualizing the Tintina once upon a time coming through that map as well? And it's just been concealed?
Oh, sure. It's underneath the Lewis thrust. Yeah, you can, underneath the belt supergroup, you can see it.
Huh.
You can see you can see here's Flathead Lake, I think. No, maybe that's not Flathead Lake. Maybe it is. Flathead Lake is right here, up here, one of these valleys, and it's just got a little bit of belt in it. So what's happened apparently is, this 6 or 8 kilometers of rock is eroded very rapidly from this, and you're back almost to the level of seeing through the belt. The belt is just is all collapsed and broken in little fault blocks and stuff underneath this in the Rocky Mountain Trench.
Interesting. Thank you.
And the thing to look at, if you really want to know, you can go on to the Canadian Survey's website and find God, I'm going to have a senior moment now that I want to find the name, the Fernie map sheet of Ray Price, and
okay,
stuff cutting right across the thing. And that's why everybody said, no, there can't be a strike slip fault is there, because they have belt parcel and other rock cutting right across the topographic feature of the Rocky Mountain Trench.
Well, I don't want to derail you too much here, Bob, but like we're looking at that map and that you've got everything to the west moving north. And so
no, I'm not have anything moving north on this map.
To the west of this, everything from this point to the Pacific Ocean, you have moving north. And I'm visualizing.
No, you're putting words in my mouth,
Bob.
I'm telling you, only from the trace of the Rocky Mountain Trench westward. This is a thrust fault. This moved eastward and was in place to the east on North America. All of these thrusts are from west to east.
I'm talking on a larger scale right now, remembering your Cordilleran maps and this motion, and I'm just trying to find where that Tintina is coming through here, and you're saying it's not right at the red line, it's a little bit to the west of the red line.
Well, it's definitely to the west of the well line. I have it covered up as to where is that the lake blue? Is that blue? That blue might be, it seems a little bit big, but somewhere right through here is where it comes. Yeah.
Thank you. Thank you.
Yeah. It's where it's the Rocky Mountain Trench, and the Rocky Mountain Trench, I can go back to 4 or 5 slides and refresh your memory. Let's do that. Because it's easy to do. Here's Flathead Lake. Here's the U.S. border.
Yeah.
So it's coming right down through here, comes right down through here. Oops, sorry.
Okay.
Comes right down through here, right? That's where it goes. The Lewis Thrust is out here.
Got it. Thank you. We're at the top of the hour, and viewers, we're going to come to your live questions. And I don't know, Bob, can we do like 10 more minutes and then get to some viewer questions, please?
Well, let's see what we can do.
Okay, thank you.
So an important thing is to notice that the Ochoco Basin, which Bernie Housen and Ms. Dorsey suggested had 1760 plus or minus 460 kilometers of northward movement. And it's actually was bonded by about 100 years to the Idaho batholith and the Belt Purcell. So here's a bit more evidence that the Belt Purcell has moved northward along with the Ochoco Basin and everything else to the west. If you go down to Baja, and here's uncorrected paleomag from Baja from Bill Dickinson and Butler. And notice the thing is, if you look at Baja in Southern California, you see that the farthest stuff is about 70 million years old, and then it converges with the North American craton by 50 million years. So you can see that this is everywhere from the Carmacks all the way to Baja. Southern California's got about the same kind of paleomag signature. Nothing special. Mm-hmm. So the point I wanted to make, and I'll make it as quickly as possible, is that if we're going to move this stuff back, in other words, we're going to move this red back to this red. The area that's moved is moved right past this area of Laramide thick-skin deformation. It's basically a hit and run, but much younger than Basil's. This is a 70 to 50 million year, and Basil wants to do something at 100 million years. But the Carmacks is 70 million years, and it's got as much motion as anything. So, but it formed a whole bunch of basins, and they only occur in between the Lewis and Clark lineament and the Texas lineament. So the timing on those basins, they all formed in the Maastrichtian about 70 million years ago, 71 million years ago. And they all died out in the Eocene. Again, same time as we're talking about, 70 to 50. So I like to relate them. And if you look at the sedimentology, this is from a guy named Can Cantaneu, who's at Steve Johnson's department, as a sedimentologist. You can see down the south, this is Salt Lake. This is the hinge lines of the basin that's formed because of loading due to thrusting. You can see it migrates northward from the early Campanian on up through into the late Maastrichtian. Everything's migrating northward. Thrusts are migrating northward. The angle of convergence is also rotating and becoming more and more northward with time. And if you look at Roberts and Kirschbaum's USGS work, they found that you got a big basin here and down in Mexico here to about 79 to 72. It's starting to already migrate to the north. 72 to 65, of course, it's really cranking 15 kilometers of sedimentation up here. So here again, during this period, 70 to 50, everything's migrating to the north. And if you look at the orientation of the thick-skinned Laramide uplifts, you'd find that they start out in a Campanian north-south, suggesting east-west convergence, and they start to rotate around by the Paleocene. And then by 56 to 34, they're showing due north-south compression. This is from Robbie Grease, former president of GSA, her interesting paper on the uplifts in the Rocky Mountain foreland. And so the thin skin thrusts, they pretty much died off by 73. Here's the Crawford and Absarokas in Wyoming. This is the Wyoming-Utah border, and they got big fans going right across them that are about 70 million years. So after the 73 million year thrusts, the thin skin thrusts had died out. And you can just look at a cross section here. This is the stuff here we're talking about. Earlier, you had the peninsular ranges and the laramide early skin, the thin skin stuff, and then the thick skin stuff is up here at the top. Wind River uplift, all these big things here. The Wasatch Formation, of course, where we had the conglomerates, were in the Wasatch Formation. But clearly, both sides active. So the deal is this. I want to bring this stuff back down to here. It restores this beautiful band of magmatism here, the late Cretaceous, early Cenozoic, and it's slab failure magmatism. I'll just show you this here real quickly. Notice that this is Mexico, Idaho, Coast Plutonic Complex 77 to 62. They're all rocks that are latest Cretaceous, earliest Cenozoic, and they all look like good slab failure rocks. And here you can see the Carmax. We'd suggest that the Carmax, along with the Middle Fork caldera, which is just to the north, 67 million year caldera. Nobody has sampled that except for geochemistry. These also look like slab failure. They don't look like basalts, the Columbia River basalts at all. And at the same time, as I'm placing these plutons, you have major exhumation. This is time versus temperature. So these rocks are cooling fast in this range, 70 to 65 or so. Same with all of these locations. We don't have to dwell on them, but just to note that they're cooling rapidly in the sort of 75, 70, 65 realm. And all the K argon from all the plutons of that age, they're all cooling at that age. The biotites are in red. The hornblends, which are will give a slightly older age, are in blues here. But all 80 to say 65 or something like that. And up here, all areas you can see go down to about 55. So this is an origin. This is a big origin. This is what I call the Laramide origin, and it goes from Alaska. Actually goes all the way down South America. Here's a Canadian exhumation at that age, the latest Cretaceous, early Cenozoic period that was identified by Dick Armstrong first, and it goes right through the whole Coast Plutonic complex. So let's leave it there. And the point of this is that I think that there is another basin and another collision, which is the Laramide collision. It goes the length of North America. It's pretty much like the peninsular ranges and the severe orogenies before them. We don't know the width of this basin. We don't know much about the sedimentology of this basin. I couldn't tell you the polarity of subduction, although I suspect it could be westward, but I can't tell you. And as the sea plates reoriented themselves, they started to really move progressively things along the margin to the north. And this fault went up through western U.S. And then went through Canada, where it's preserved as the Tintina Fault. So that's sort of the story.
Thank you. That was beautifully done. There's many visuals probably that we could continue with, but let's see what the viewers want to ask, and then we can kind of, right now I've got your slides hidden, but we can go back to those slides anytime.
No, we're done with those.
Okay. All right.
The only thing I have left are the things for our later discussion that we were going to discuss.
Okay. Viewers, uppercase, please. Anything that you'd like. It's okay to ask for something again. Certainly, those are lots of major ideas there, and it's totally fine if you're scratching your head. Matt asks, Paleomag says the Sierra Nevada didn't move much, and yet it is between the lineaments and to the west. Do you have an explanation?
Sure.
You do? Well, I'd love to hear it.
Oh, you want to know the explanation? Sorry, I had you up on the other screen, and I was because I was looking to see if I could see if there was questions.
Okay.
So one of the things, people collected plutonic samples from the Sierra Nevada, west of Yosemite Valley, and they concluded there was 500 plus some amount of error, but they collected plutons. I don't. Where's their paleo horizontals? I know that they collected plutons that are dated to be pre 100 and post 100 million years, yet they have the same paleomag, which says they must have been magnetized later. Maybe the thing is so hot and juicy that it is completely remagnetized by its own fluids. I don't know the answer to it, but I wouldn't rely on those. It needs to get out and look at some of the sedimentary successions, the Cretaceous stuff that's along the margins of the Sierra Nevada at the south end and the Tehachapi's, or maybe some of the Great Valley. The earliest Great Valley is older than 70 million years.
Okay, very good. Thank you. Let's keep moving. Cindy wonders, could some of the unconformity missing rock periods actually be movement of large sections of rock?
Well, normally we go up and we look and see whether there's evidence of a fault or not. And that would include some kind of fault gouge, slickened sides, some kind of brecciated rock or something like that would show that there was motion. Unconformity is nothing but a buried erosional surface. And that's the definition of an unconformity. It's a buried erosional surface. So it's just going to look like something's eroded. It's not necessarily going to have any evidence for deformation. Somebody was asking a question about the 706 line.
Yeah, that's the next question. Kay Edmondson, how close does the Lewis Fault follow the 706 line?
Well, nothing to do with it. Not remotely the same. So the 706 line has generally been considered to represent the 706 isopleth, as it's called, is considered to represent the western margin of North American cratonic crust, which is supposed to be old and enriched. And the idea originally was that arc magmas dipping beneath western North America, excuse me, my daughter and wife are arriving, and so things are dipping underneath North America. These arc magmas then rose up first on the western margin where there was no cratonic lithosphere, and they gave you more primitive values. Then the slab shallowed a little bit, started to involve the cratonic crust, and so melted cratonic crust and got strontium values that are above 706. So that was the idea. But our work shows that and also ties in with the work that Robinson Cecile was doing too in the coast plutonic complexes and others. So what happens is, in our model, those rocks that people thought were due to arc magmas rising into the crust and melting the crust actually turn out to be the slab failure rocks derived from the mantle. And they come through what's called the subcontinental lithospheric mantle. And that's a big keel to cratons. Old cratons have this big keel that kind of floats around with them. And it seems to be enriched by older fluids and arc magmatism and things. And so when you bring magmas through this old enriched cratonic lithosphere, they grab onto the parts that they want and they suck them in and they change their isotopic composition. So in our book, the 706 line actually represents the edge of the slab failure magmatism to the west. And that's why when you go to the coast plutonic complex in British Columbia, where there is no old enriched lithospheric crust, cratonic lithosphere, the isotope ratios are like you find in arcs. They're primitive because there's nothing that's old and enriched there. So you can have both in slab failure magmatism. I don't think you can get both in arc magmatism, and it's a bit of a misnomer what the 706 line is. Joe and I need to write a paper on that actually one of these days, and a short little note of some kind.
Thank you. Michael says, you mentioned last time that you would explain the Western Interior Seaway. How does this fit into the story? I know you've got a huge paper on that, but can you boil down some? You were doing a little bit of that today, right? Those isopachs were were from sediments in the Western Interior Seaway or not?
Right, they were. And what happens is our argument was that the western edge of North America was subducted beneath the Peninsula Range's composite terrain at 100 million years. The Western Interior Basin during that period was the orogenic foredeep, and was receiving sediment from both sides, actually, both the Crotonic side and the west side. And you can see the sediments coming from both sides, and they come from different sides at different times. You really need to read the paper. It's CJES paper 3. It's kind of the standalone paper on the Western Interior Basin.
They've got it from the last show. That's part 3 of that
was there.
slant thing. Yeah. Papagino wonders, is Rubio and Subian the same idea? Yeah,
we could, and Karen Sigo, so if we go to this next little section, we can cover some of this ground. We could do about a 10-minute section on this, because you want to know where the sutures were anyways. And Ruby and Sabier, we have to deal with those sutures, of course. So it's up to you if you want to do it. I got some slides queued up. We could look through a couple of those, and I could show you what I think you were having a problem with the other day. Oops. Okay. Well, let me go first, and this is not really what we're talking about, but this is an equatorial section of the Earth, and it's kind of cool because there are, and I don't know how many people know this, but there are 2 areas called Jason and Tuzo where slabs, and where the edge of plumes rise. So they rise up here and they rise up here, and then on this side, and they're supposed to be been in the same place with respect to the inner core since, I don't know, since the Precambrian. So Joe and I argued in a 2014 paper on Peru and South America that there was a fixed arc out here. It's exactly what Karen Siglock's has argued about at about the same time. And she did it from tomography, and we did it from the geology. And we said there's probably some complementary downwelling zones that to offset these 2 upwelling zones on here. So on both sides of the Earth, you'd find long-standing downwelling zones. Enough of that, though. But it shows how similar our models really are. And Karen will cut it off in the Jurassic, but we take it down into the Cretaceous.
Okay.
Let me. There's some things in the way. I thought I had sorted them out here, but I guess, and I'm just going to flip through these because they shouldn't be here. And well, no, they weren't part of this talk. And
I got you. We're good. We're good. Oh, I love that one.
Yeah, that one's good. But we showed that one the other day. So I got the Eocene. I don't know why. Sorry about this, folks.
Okay, this is.
Somebody can go through and see all these figures later on. So let's see if we can get. I think we're getting somewhere now. Okay, I wanted to show you. We were talking. I mentioned Nevada the other day, and I said, it's not quite so straightforward as you think. So I'm going to take Nevada here, and this is a complicated figure from my paper, and I didn't want to redraft it for a slide. So I thought I'd flip it up on its side and confuse you all the more, and show that I just want to show you the kinds of complexities that we're dealing with here. So this is the looning fence maker thrust through here. It's the separation separates the green from the blue, if you can't see my cursor. These are Jurassic rocks. These striped rocks through here are arc rocks, 100 to 130 million year arc rocks. This fault marks the edge of it. And there's all kinds of 4039 argon that says that this was deformed or exhumed and cooled at 100 million years. So this thrust looks like a 100 million year thrust, although, there's no other way to know it except for that. Then you have what's known as the Golconda allochthon, and its age thrust is not known, but it's exotic rocks, mainly Paleozoic to Triassic. Then you have a belt of lower Cambrian and lower Paleozoic rocks, which comes to a very narrow belt that comes to here. It's completely different from anything else. The detrital zircons, everything looks different. Nothing looks like this. Then you come to this some basinal facies with all kinds of weird basinal facing ribbon cherts and things, and some Jurassic rocks stuck in the middle of it, little volcanic piles here and there, and sediment on top of it. Then you come out here and you've got the 124 million year thrusts with basins. And then by the time you're at the Spring Mountains here, you've got 100 million year thrusts. Then you got a belt of sedimentary rocks here in the White Inyos and the Esmeralda that's completely different from everything else. And the rocks in Death Valley going over to Las Vegas, the Cambrian and late Precambrian rocks, they're all different. So there's a lot of complications. It's not like you can just go and put your foot. If you go to westernmost Utah, the House Range is here, 3,000-foot cliffs of Cambrian carbonates with a Jurassic intrusion in that space. Great place to go. I recommend anybody go to the West Desert of Utah. The mountains out there are higher than the Wasatch. Beautiful place to go. Right there, there's a shale basin. Starts right there on the west side of the House Range. This is what Steve Johnson, this is what I originally wanted to have movement in. No one knows anything about, no one knows what this boundary is. It's not exposed even, but you just go, here you're in shales and deep water sediments, and here you're up on the carbonate platform. And this you see wherever you see these kinds of rocks up and down the Cordillera, and that's what Steve Johnson is all about, and that's what we talked about. And then you go further west from that shale basin, you come to another shelf. I call it the Antler Shelf down here, and in Canada it's called the Cassiar Platform. And it's different again. So you go, wait a minute. I thought back here I was on the North American platform. Then I go out into this basin with some kind of a structure here, and then I'm onto another west-facing platform. And then I go a little bit farther east from the House Range, and I see that the seismic shows that there's huge normal faults that go all the way from the thrust belt. This is kilometers, mind you, all the way to the thrust belt out into Nevada. And they have like 60 to 80 kilometers of normal fault displacement on them. And you kind of go, wait a minute. So everything's been on the top of that fault has been moved west from the thrust belt. And that's young. That's much younger than any of the movement that we're talking about going north. So that kind of thing, you wouldn't even know where to look to find the fault down here. I think I do, but you have a hard time because this normal fault and all this westward movement postdates that any movement of the northward stuff that we want to talk about. So continental margin looks like this. I'm showing it purposely facing east. And you can rotate it later if you want. I want you to think the concept, not the place. And you have a continental shelf platform and then a steep slope, although this is what it looks like in real cross-section down at the bottom. And then the continental rise then out sediments onto the abyssal plain of oceanic lithosphere. This is what it looks like. This is your passive margin, the west coast, the east coast of the United States. Australian passive margins over here, opening of the Atlantic. So east of this passive margin, what's there? Nick, what's there?
Deep ocean.
Okay, so here's your passive margin. Here's a west-facing passive margin with the carbonate platform on top of it. It's like we showed in the other talk. During the Cambrian, North America was completely rimmed by carbonate platforms. It was a peneplain. It hardly had any significant hounds. There were no clastic rocks being derived from it. So this blue belt here represents the fold and thrust belt of rocks sitting on the hinge line. In other words, on the edge of the platform. They're North American platformal rocks that have been thrust up on here. Everything outboard of that platform is certainly suspect, right? Because it's oceanic. So this you were quite shocked the other day and saying, oh my God, this is radical. You called it crazy, as a matter of fact, to quote you. But this is the carbonate platform and the passive margin of North America. Everything outboard is stuff that's come in. It just has come in at different times. And so it's when you like it to come in is your sort of what flavor you like. Here's a cross section. Here's a North American platform here with the shelf edge. Then there's some kind of thrust fault here. Thick basinal sediments, although they seem to be dominated by the Permian Pennsylvanian. But then you come out here under the Antler platform again. You've got another platform, and that's got the Neoproterozoic Windermere rocks and these things underneath it. And it's also got rocks related to the Roberts Mountain Lockdown. So it's the first thing that collided with the Antler platform to the west, way back. Anyway, so this is the edge of North America here.
Hmm.
And if you go out to the Antler platform, what you find, it has a lower Cambrian carbonate platform with these type of animals called archaeocyathids. And if you go to the North American platform side, that's a middle Cambrian. It's quite a bit younger and middle Cambrian, and has typical, Cambrian reef type stuff in it. So the platforms are different ages, the carbonates. And some people might say, oh yeah, well, it prograded onto North America. Well, that doesn't explain the big belt of shales in the middle. And I'll skip that. The Windermere I'll skip. We won't talk about. Here's the same section in Canada. Note you got a big Cambrian, shelf edge here. And then you go out across the break into the Belt Purcell, the Windermere, and some rocks on top of it. But it's the same story, though. And here's an image that I made to show you Steve Johnson's basin. This is his shale basin here from his 2008 paper, actually. The Cassiar platform in dark blue out here, the Selwyn Basin, Kachika Trough. And remember, this is where we were looking at our sections of the two thrust belts. Crossing was right in here as well. Then the Rocky Mountain platform, which is clearly North American. So Steve's idea and my original idea was, look, you have this break is within this shale basin. Now, of course, now it's got the Tintina Fault that cuts across it all and makes it complicated. If you look at the Canadian edge of the base of the platform, it's got platform edge and then all this debris being shed off the platform into deep water. And the funny thing is that when you go and you look at rocks, these blue are supposedly part of North America, but they're not all because they're west of the Rocky Mountain Trench. You got the Fang Stock here. The Fang Stock is right next to this Windermere. This Windermere is all polydeformed during the Jurassic and then slammed against these rocks here. But these rocks were never deformed during the Jurassic. They have overturned limbs of folds. Look at this fold here. This is a refolded fold. Comes around. There's the fold nose. There's another one that comes around, comes up here, and then on up through here. This is do I not have the scale? This is about 30 kilometers across, just that overturned fold alone. And it's just juxtaposed across the Rocky Mountain Trench, which is here, by a little bitty thrust that crosses it, called the Purcell thrust, and into more upright structures of the passive margin. And here's the Fang Stock. It's got 6 kilometers of uplift, and it's supposed to be adjacent to the North American Craton. So all this stuff looks like it's outboard. It's all outboard stuff to me. And I've written a couple of books on it. And so here's all the various terrains. You can see the Selwyn Basin's here. And then you right away, boom, into the Yukon Tanana and out here into Kootenay and other rocks out here, Kithanelli and so forth. So they're all outboard, completely outboard of North America. So did that answer that question, or did we not get to that question?
No, you did a nice job. I see the complexity. I think I'm interested in, we're 8 years ago that you're publishing in 2015, that paper, that map that we just saw, this elegant offset of those lineaments. Can you summarize the reaction that you've received over the last 8 years? It's so nice and tidy and visually appealing. Why do people have a problem with what you're saying?
I don't know that they do.
Right.
You'd want to talk to them, not me. I'm not going to, I could tell you that some people like it and some people don't. Eldridge Moore's said, aha.
Okay. What do people say when they don't like it? I'm just curious what you've heard. If you want me just to talk to them directly, that's fine.
They don't say anything. They don't talk about it. They don't cite it. They don't say anything. What do you mean?
Well, I don't even know why we're having a series talking about all these models. If that's the one that is. Let me try this. How are you viewing this differently than Stephen Johnston? Or are you guys in lockstep and seeing things identically?
I don't. like Mott Green, the scientific historian who wrote a wonderful biography of Wegener, said, everybody that is capable of developing a tectonic model will do so.
Yeah.
So everybody, all of us are going to, that you're talking to, are making tectonic models, and Steve has one. And first I didn't even know about Steve, and he didn't know about me, and we were working on it. And his paper predated mine. It was 2008, and mine came out in 2009. But obviously, we were both working on them at the same time on the ribbon continents. And I didn't know about him, and he didn't know about me, like I say. And so we came up with a pretty similar model. I mean, we moved the contact here or there, but by and large, we had one large ribbon continent. I've since found that there's several pieces. There's fragments. They're not terrains really, but they're fragments of things that have hit with North America and then rifted off again. And so that's why this terrain notion is kind of misleading to people. Talking about the insular and intermontane, they were together since 225 million years ago, according to the Paleomag of Kent and Irving. So they docked in the Jurassic with Western North America, and then things split open, and you got pieces of this, pieces of that on each side, and so the terrain concept becomes just nonsensical because it's a puzzle, and things have moved at different times and different places, and then you have things moving to the north, and so it's not so straightforward. And most people, just like yourself, you're there the other day going, damn it, I'm from the United States, I'm from the lower 48, I want to know about the lower 48. Well, the Canadians are up there going, yeah, I want to know about Canada, and the Mexicans are going, Viva Mexico, and so everybody wants their own thing, but few people want to look at the whole thing. Basil wants to look at as much as he can. Steve Johnson wants to look as much as he can. Most people are not. You talk to them, their eyes will just kind of glaze over, and you'll see that they're, oh my God, Hildebrand's just going on about all this stuff, and because I have a lot of data that points to these problems, and so. It's hard. People, if you don't know the geography, which is you were strained about the geography, so it's hard for us to have that communication without figures which show you the geography. I know it in my head. I've been there. It's embroiled in my brain. I've probably taken photographs there, and so it's different than somebody who hasn't been there. And so that's why I insist on showing some graphics, because just the geography is difficult to get by. It's hard to for people that don't know it to get through it. So other people, I mean, I don't think it's obvious that they don't like it. There's a group of Cordilleran geologists that are fixists. They don't want to move anything. Jim Monger thinks that the entire Cordillera was formed just by subduction, eastward subduction of the Pacific Ocean, and occasionally it brought in terrain and it glommed onto Western North America, and that was it. But that doesn't seem like a very satisfying model, because there's more to it than that. And so the idea of several different terrains or blocks, these ribbons like thing, that's where I would go now. And Stephen hasn't done much with it because he's been department chair and his research abilities have been limited. He's been focused on his research time, not abilities. He's extremely able and competent, but he's been working over in Europe on the Harrisonide stuff and thinking about Alaska and that stuff. He hasn't been thinking that much about this. And so I'm kind of the only lone bird that's thinking about this. Nobody else is, writing on it so much.
I assumed that you and Stephen Johnston were communicating about these ribbon ideas 15 years ago. You're saying you didn't know each other at all? Like, that's such a crazy coincidence.
We didn't know each other. We didn't know we were working on it. No, we didn't know any of that.
Was there some new data set that spurred both of you to think at the same time? That just seems almost impossible to visualize that model would come from two completely different guys simultaneously. It really was just coincidence?
Yeah, I think it's happened before in science. I mean, I think people have come up with the same idea roughly in different places, and there's when there's as sort of things that argue against it come up, more and more of them sort of come up, little things, and people notice little problems with it, and eventually it becomes like a Kuhnian revolution of some sort of, I don't know whether he's really right or not, but about scientific paradigms. But You know, that so they're defended till the end, right? And so, you know, there's people out there who are you know, well known and reputable people, and they just don't see anything. They draw a line from Wyoming and they go right out past the Franciscan and they say, here's our cross section. And Stephen and I and a lot of people that don't specifically work in the Cordillera generally are think that that's a problem. We don't know any. I couldn't tell you any place, and I'm sure Stephen would tell you the same thing. We don't know any place where you can draw a section through the Cordillera where it would reflect everything that was part of North America. It's chopped up and gone and moved around, and basins have opened up and closed. Pieces of one side have ended up on another side. That's why this paleomag becomes a problem. That slide that you really liked, where I had the little pieces of insular stuck on the peninsular ranges composite terrain and vice versa. Well, if you did paleomag from that arc and it was sitting north 500 kilometers, and then you brought it in and you thought it was there all the time, you'd say, well, why is there this big sinistral slip? See, and that's why I thought that it was advantageous to solve the Carmax first. Excuse me, because that gives you the biggest chunk. That gives you everything. And then if you go and tack a little bit onto the older rocks, or if you want to investigate the 100 million year arc rocks of Thorkelson that have that weird, everybody wants to make sinistral, that you may not even need to make sinistral, if that could be on the west side, and it could have been come from the north, and when it docked with North America again, it had paleomag from when it was made. So, but that's a different part of the problem, I think. And if you try to resolve it all at one time, it's too much. It's too complicated. There's too many paleomag stuff. There's too many fragments and pieces all moving around and jumbled. So that's why I said, no, let's start in the east with the Carmax and the Tintina Fault. If the Tintina Fault has 1,950 kilometers of slip, we should see it. We should be able to find it. It should not be impossible. There is a problem to be solved. And so that's what I set out to do after I realized that last year that you know, it had to be the Carmax. The Carmax told you the story, and all the slip was on the Tintina Rocky Mountain Trench. And then I realized,
are you going to continue working on the Tintina then? What's next for you?
I'm writing a paper right now on it. I don't, you know, I mean, I've got mostly done. I have to continue. I've got it written. I probably have to. I'm still working on the U.S. sector, but otherwise it's been pretty well done. Yeah. That's why I didn't comment on the U.S. sector really at all, because I don't want to spill all my beans.
I got you.
Get it out there a little bit.
Okay.
But you know, there's let's just put it this way: there's most of the Western U.S. is, you know, not even exposed. There's huge basins down. You can run, you know, whatever you want through those basins in many places. You just need to find the proper discontinuities, and they exist. But go ahead.
Go ahead. Well, I have one last question. I think we should wrap up. You've given us a lot of your valuable time, and the next episode we're heading to the Klamath, and we've flirted with the Klamath a little bit here and there. I was intrigued by your slide when we were having trouble last show. I'm not sure we had audio even at that point, but you showed the Sierra Nevada batholith, or the Sierra Nevada area, and the Klamath being joined and then rifted away from each other 140. Did I catch that correctly?
Yeah, you did actually. They have a pretty common history. That's pretty well known. They have a common history up to about 140, and then after that, those post-collisional plutons come in both terrains. They separate, and you don't have any of the Cretaceous arc rocks of, I mean, the say 135 to 100 million year rocks in the Klamath. They just don't even appear.
Do you have the Klamath going way out into the water then?
Well, they go out somewhat. I don't know how far they go, but you know, there's a basin, the Hornbrook Basin, on the east side of it, which is debris from the. It's full of. We showed it in the talk the other day. If you go back to look at the detrital zircons I didn't talk about two basins, but they were in the right-hand column, and one was the Hornbrook and one was the Ochoco. And both of those basins are filled with 100 to 90 million year detrital zircon. So they were on the west side probably of the uplifted collision zone. And so the Hornbrook is actually unconformably on the Klamaths. So it looks as though that little piece of Klamaths could have been part of the basin that headed off to the west, or the western origin of that basin that headed off to the west. But it's got the Hornbrook on it unconformably, and so that's all you can say. You don't know really where it went.
Is that the same vintage as the Methow Ocean?
No, the Methow
totally different.
130 and 100. The Methow's the Arc basin, and we showed that. We showed how the deposits were arc-like in composition. The Methow is 130 to 100. It's got these big peaks at 115, 116, and it's on the Jurassic basement. So the Ochoco and the Hornbrook are the same age as the Nanaimo, the Eastern Great Valley, the Valle, and the McHugh in Alaska. And they're all on the west side of the collision zone, and they get these post-collisional zircons made up of derived from the post-collisional plutons.
Huh.
So you got on both sides is what so don't get confused and about that, and because that's an important point. I was looking for one slide for you but I don't
go ahead and look. Like I don't know if you feel like
bring in one slide.
Sure.
Can you do that?
It's black.
It's black.
Do another.
Let's forget it then. It's not worth it.
Okay. I want to thank you for a number of things, including, did you make a few slides specifically for us? Like, there's some things that I hadn't seen before. Were you making a?
I'm always, if I want to show a figure, I'm not going to, most of the time, unless it's too complicated, I'm going to make a slide out of it so that you can see it. I mean, I did some from Montana and some like those ones for the belt with the sediments and I was showing where they were and stuff. It doesn't take very long. You just whip them out and so.
Well, we really appreciate it. That extra effort for us.
It's not extra effort. It's what you do. If you're giving a talk, you make slides that if you can, that people can read and make sense out of. It's not like it's anything special. You just do it.
I'm thanking you, Bob. I'm thanking you for putting energy into this. Thank you.
It's like it's like my daughter. I mean, maybe I have this peculiarity, but so my daughter's. I watch these girls playing softball, and all the parents are there, and this ball's over their head. Pitcher throws the ball, it's over their head, and they go, "Good eye." I just think it's what they do. They don't swing at balls over their head. It's not a good eye. There's nothing to do with that. If it was like just outside or just inside, maybe at the right level, it's a good eye. But so I'm thinking like, to make a slide is like sort of a normal thing. You just sort of do it. So, I don't know. I enjoy doing them too. I can sit down and space out on the slide, and I mean, I don't even use drugs or alcohol or anything like that to do it either. And so it just happens. So I enjoy it, and I appreciate. I like being able to show people, and I'm happy to educate people and help people out with this stuff. Anytime I can. So.
Thank you, Bob. Thank you. Well, you've done tremendous stuff here for the last two shows, and thank you so much for all that energy, and we'll look for you down the road. How about that?
Okay, whenever I'm here. At least for now, I'm still here.
Okay.
How long? No saying how long.
Okay. Well, good luck. Thank you. Bye-bye. Well, that was a sober Bob Hildebrand, apparently. Drug-free, alcohol-free, clear of eye, clear of mind. And I hope that you enjoyed both of those shows. There's plenty to absorb, for sure. And yes, part of the story, much to my surprise, was the thin-skinned thrust faulting of last winter. But if I really had thought about it, it shouldn't have been that big a surprise. Let's go to the laptop and simply just show you the papers that Bob selected for you today. Make sure that you know about those. And we'll probably call it a day. We go to nickzentner.com, of course. We click on the word Baja in the upper right-hand corner. You know the drill by now. And what do we have now? 1, 2, 3, 4, 5, 6, 7 Hildebrand papers, and many of those papers are 50 pages, 100 pages, even more. So there is all sorts waiting for you. The key paper is a short one that really made the rounds, and this is the one to correspond with a number of the things Bob was talking about today, including this map that I cut up here at the beginning of our program today. And if you didn't catch what I was trying to do, or if you didn't catch what Bob was saying, here are the thrust faults in the Canadian Rockies. And Hildebrand is wondering if we can take these guys and get them back down here. And therefore, these black things are the block uplifts of the Laramide in Wyoming and Colorado, and a little bit of like the block uplifts in the southwestern Montana area as well. And then once we get north of the Lewis and Clark zone, there's no more block uplifts. I didn't mention at the beginning, but is it a coincidence that Basil, who has the western Idaho shear zone right here, remember Basil is, with the hit and run model, is docking insular no farther north than Idaho. Remember, Idaho and point south is where he hits. And here's our block uplifts inland. Is that a coincidence or not? This is the paper from the previous year. So we're back, almost 10 years ago now. This is 2014. And Bob is making cases for westward subduction. And this is that green map that I was looking at with the laptop last time, the one that I turned on its side. There's the mismatched geology that I really don't have a good sense of how much you were able to follow today. I'll enjoy reading your live comments. And then 10 years ago, this is the first of the two major books. So some of you have noticed me holding up these two thick books, and you're like, how can I get a hold of that? Well, you've got them. Bob has given us the PDF file. Look at the 179 pages. So he's not kidding when he says it's a book. But the 2013, the 2017 are special papers which are incredibly rich in detail and feature these major illustrations, cross-sections, and so on from Dr. Robert S. Hildebrand. I cut it short, but I was even going to cut one of these. I've got a few of these. I was going to. I'll keep it. I won't cut it. I don't know if these are available for purchase still or what, but these are the two quote unquote books that Bob was talking about. And just like the old National Geographics, there's maps folded inside. So you can get kind of poster-sized versions of area north of Yellowstone. And there's our friend today. Both of these are friends, actually, from today. I want to say a couple of closing thoughts, make a couple quick announcements, and then I will toast you. How many do we still have? We still have more than 700 watching. Where are we in the series? Well, there's two ways to answer that. One is to show you the schedule and show you the next few guests that I have lined up, and I'll do that in a second. But I think the first thing I want to do is a verbal, where are we in the series? You're still watching the series, so thank you. You haven't bailed on us completely. I knew that when I interviewed Bob, we would be as wide, as deep, as far-ranging, as creative as we were going to get when talking about Baja BC. Again, we were talking Alaska to Mexico today, Nicaragua to Nome, whatever. But for the remaining letters, and there are 5 more shows to finish this A to Z series, I think, I'm not sure, but I think we're going to start telescoping back down. We're going to go smaller and smaller, or at least be back to kind of similar things that we were doing before the holidays. If you remember, we spent 4 shows just in the Nanaimo Basin, looking at the detrital zircons, and we'll be returning to those kinds of smaller scale studies that are important, that are interesting, but my point is we're not going to go to Mars next or whatever. We're going to bring it back just a little bit, for better or for worse. And if you're a longtime fan of the channel, you know that's a theme that I've had almost always. I think I mention it regularly. I'm a fan of changing scales on purpose regularly. Okay, I'm going to learn something very small. The contact between the Stewart Range and the Ingalls. Okay, now I got to go bigger to see what that means. And then I'm out broad, and now I want to come back in and look at some detail again. That's the way I operate. I keep zooming in and out, and I think that's helpful from a teaching point of view. I do that in my classes. We zoom out, we zoom in, we zoom out, we zoom in over the course of an entire class. And we've been zoomed out to the extreme. It's time to zoom back in. So what are the zoomed in? I think, who knows, but I think that's what we're doing. The next few shows, let's look at the schedule. First of all, the standard calendar look. We are about to wrap up session U, and the next time I see you will be Saturday morning, February 4th, 2023 at 9 a.m. Pacific time. W, X, Y, and Z. Well, I don't have the last 2 shows figured out yet, but I have the next 3, and here they are. So you are cordially invited to come back on Saturday morning at 9 a.m. Pacific, and we will visit with Erica Boudreau and Rich Gashnig. Erica is a graduate student at University of Massachusetts Lowell, and Rich is her advisor, faculty member at UMass Lowell. And Erica just finished a master's degree on the Gold Beach terrain in southwestern Oregon with Rich's supervision. So I'm going to have both of them on at the same time. We're going to start thinking about southwestern Oregon in the kind of framework of Baja BC, and I'm looking forward to that show. And a week from today, we're going to visit with Joanne Nelson. Never met her. I can't even say what her affiliation is. That's how much I know about her. But I was tipped off by Randy Enkin and a few others that Joanne would be a good addition to the series for a number of reasons. And so I'm going to meet her virtually tomorrow morning as we test the AV, and I'll start to get some vision about what we'll do with Joanne a week from today. We'll be talking about Northern Canada geology from her career. And then Chris Mattinson, some of you know from last winter, and Chris is one floor up, and I suppose he'll be sitting in his office Saturday, February 11th, doing a virtual interview with me, even though we're in the same building. I think that's what we're going to do. And still unsure what Chris is wanting to do. We've been talking in the hallway about the series almost every show. So he's been watching, and he has all sorts of ideas. And then, I don't know, still trying to figure out how to wrap things up. And my final announcement is that I just inked in some dates, and I want to give those that are interested a little heads up. It's been 3 years. It's been 4 years since I did some downtown geology lectures live in an auditorium. And I'm going to do it 4 nights in a row in late March. So for those that want plenty of heads up, if you want to come to Ellensburg and listen to a live lecture, I'm going 4 nights in a row, 7 p.m. at a place called the Morgan Auditorium, which is on First Street here in Ellensburg. And I have no idea what I'm going to talk about. I have no idea, AV, whatever. I don't know. I'm still thinking about it. But this is a start. And those that might be traveling in to town from far away, I wanted to give you as much notice as possible. So I don't think I'll talk about this again, maybe till I wrap up the series. But please know that I have 4 live lectures coming in downtown Ellensburg in late March, and it's free and open to anybody that wants to come. A toast to you. Where's your drink, man? Here's to you for joining us today. Thank you very much. Here's to our guest, Bob Hildebrand from Tucson, Arizona. Thank you, Bob, for your time today and also on Saturday morning. Here's to your health and everyone in your community. Tonight. Thanks, everybody. Hope you enjoyed the show, and I'll see you Saturday morning at 9 a.m. with Erica and Rich talking about Southwestern Oregon geology. How much do I know? Almost nothing. So I've got some reading to do between now and then. Thank you. I love you. And goodbye from an overcast, dark, cold, and yet cozy Ellensburg, Washington, USA. And the students are out in the hallway waving right now behind a locked door. I need to go let them in, and we can talk about this together. I don't think they were watching. I think they were in the lab room across the way, but they'll want to come in, and they've always been asking to come in and take a look at all this setup here. So I think it's time to let them in. Thank you. Goodbye.